Okay, so this last problem here, it says to determine the force P. So that makes this an equation of motion problem. But to draw the free body diagram and the MA diagram, we're going to have to know some accelerations. And to do that, we're going to have to do quite a bit of kinematics. So this ends up being a relative motion problem to get the accelerations. And after we do that, then we can draw the free body diagram and solve for P. So let's start with the kinematics. There's some kind of interesting things going on. We're given that the angular velocity omega of AB is 0, but the alpha is 10 radians per second squared. Often when velocity is 0, acceleration is not 0, so it's not surprising. But I think it's the first time we've done a problem with a velocity equal to 0. So anyway, let's start with the kinematics. And whenever we do the kinematics, we start with the velocity first. Okay, so as you look at this, you look for like pins and things that are spinning around pins. And so A is definitely pinned, and so that means B is spinning around A. So the velocity of B we can get if we know omega, and we know the omega is 0. So since omega is 0, the velocity of B is 0. Okay, so next, what we want to do is we're now going to use the relative motion looking at bar BD. Okay, so we can see that D is sliding on this rod here, but we don't have the rotating axes things because this rod here is not rotating. It's just staying still. So this is not one of those with the Coriolis acceleration and the rotating frame of reference. It's just a regular old relative velocity problem. So we have V of D is V of B plus D relative to B, which means D spinning around B. Okay, so what do we know about these things? Well, we know the velocity of B is 0. We just talked about that. And if you look at point D, again, that rod is not rotating. So D is definitely just sliding down at 30 degrees, right down that rod. And D relative to B means D spinning around B. So D is spinning around B, it's going downward vertically, and so you have that. So now you look at this vector equation. There is no way for a vector that's inclined at 30 degrees to equal a vector at 90 degrees. I don't care what numbers you put in there, they can't be equal. Well, the only way they can be equal actually is if they're both 0. So immediately we know that V of D is 0 and D relative to B is 0. If you wanted to use an equation, take the X component and you can see that VD is 0, and then you take the Y component and you get D relative to B is 0. But it's just impossible for two vectors that aren't in the same direction to be equal, so they both have to be 0. And because all the velocities are 0, that means omega BD is 0. So we're done with all the velocities. Everything's 0. Next, you move on to the accelerations. And by the way, these are all vector equations. Sorry. So same thing. The acceleration of D is acceleration of B, D relative to B. And let's put it in everything we know. Well, again, that rod is not rotating, so the acceleration of D is going straight down that 30-degree rod. The acceleration of B is R alpha. R is 0.9, alpha is 10, so 9 meters per second squared to the left because alpha was counterclockwise. Normally, there would be an R omega squared pointing from B to D, but omega 0, so it's not there. Okay, and so we have D relative to B. Again, that means D spinning around B. If this has an alpha clockwise, that would make this R times alpha. And normally, there would be, pun intended, a normal acceleration, R omega squared, pointing in. But again, omega BD is 0, so there's no component pointing that way. Okay, so now we have this vector equation. One way to solve it, you could do the X component and the Y component. The two unknowns are AD and alpha BD. We're trying to get this alpha BD. And you could do the two equations, or you could take like a component this way and this way. What I did is, again, just looking at the vectors, you can see that tangent of 30 degrees is y over x. So tangent of 30 degrees is the y component, 0.9 alpha BD, over the x component, 9. And so I use that equation to solve for alpha BD. Okay, but that's not the goal. The goal is to get P. And so to do that, we're going to need the free body diagram, which I've drawn right here. Okay, so here you have this horizontal link. There's the two reactions. We're at the pin, the weight, and this unknown P. And what it will have is there's going to be some MA and an I alpha. And so what we're going to need to know is what is the acceleration at this point in the middle. We do know the acceleration out at B, but we don't know the acceleration at G, okay, at the middle. So the acceleration at the middle, A of G, is A of B and G relative to B, or G spinning around B. So we went through this. The acceleration of B is 9 meters per second squared to the left. And so now G relative to B, so G's in the middle and there's B, is just G spinning around B. And again, there's no omega, so there's just this R alpha term. The distance from the pin to the middle is 0.45. The distance to the end was 0.9 times the alpha. And we just got that alpha, 5.7. You put it in there, and you can get this. So now we can write out the right-hand side. We know that the x acceleration is 9 to the left, the y acceleration is 2.6 down, and the alpha is 5.77. So we have the complete free body diagram. We want some kind of equation that will solve for P. The smart thing to do is to take moments about B, because it gets rid of those two reactions. I'm going to take clockwise as positive. So you have the weight times mg times its moment arm from point B, which is 0.45. You have the vertical component of P, which is P sine 30 degrees, or P over 2. And its distance from B is 0.9, so there's the force times the distance. And on the right-hand side, taking moments about the same point P, you have m times 2.6, okay, this one right here. And its distance from there is 0.45 meters. So there's that, times 0.45. The m times 9 goes right, it points right through B, so that doesn't have a moment. And you have this I times 5.77. You can calculate what m is, or it's given. You can calculate I. You can solve this whole thing for P, and you'd be done.